Record. Perfect. Now I'm recording. All right. Sorry about that delay, guys. All right. So last week we did our lab, and I think that was a good way to make learning on the machines a little fun. I know everyone wants to be on the machines more. I just unfortunately can't teach all the content and how to program and the concepts and have a lot of time on the machines. So like I said from the beginning of the course, it was a mostly theoretical course, but there's some definitely hands-on stuff as much as possible. It is nice to be able to apply those the lessons learned to hands-on type of applications. I think maybe you'll remember it a little bit more too when you can practice it on a machine. So the first thing I need to do for you today, because we're new to this, is I need you to download the Ivanti VPN. So I talked to IT about that today, and apparently many students download this and it's perfectly fine. So I need you to go to this link I'll put in the chat. And I need you to go to the very bottom of that link, and you have downloads for employees. It's the Ivanti Secure Client, Secure VPN client. So if you have this, it gives you access to Conestoga, essentially Conestoga's network from a remote location. It looks something like when it's installed. Please give me some thumbs up and stuff to make sure that everyone's able to navigate to that correctly. So this one right here, it looks like this once it's installed. It uses your Conestoga email and your Conestoga password. You log in. I called my connection, my new connection that I made. You just click a new connection. I don't even think I needed the server. I don't even think I did it that way. I did it a while ago now. So if anyone's having any issues with that, I'll have you share your screen so that I can help you along, and then it'll show everyone else what to do as well. Are people downloading this? If you are not, you will not be able to open the software from home. So if you do download this and you get this working, you'll be able to open the PCDMS and you'll be able to follow along today. If not, you'll have to review the recording at a later time when you have access to the network so that you can follow along with things we're learning today. Abraham, thumbs up. That means you downloaded it, or it means it's working.
Already downloaded.
Perfect. So I don't remember how the making the new connection works. So if you can help point that out, that'd be excellent.
The instructions are already there in this.
Kind of on the site, right?
It's already there.
Good. I'll give you guys a couple minutes to get this up and going. And in the meantime, I will jump over to our PowerPoint for the week. And I actually have a bit to cover from last week's PowerPoint. I never did open it last week. I just showed you all of the concepts in this PowerPoint from the software last week. So we didn't use clearance planes. I told you that that's something we're going to omit. So we'll do clearance cubes only. I showed how to activate that. I showed how to activate that. If you forgot to activate it, when you do your collision detection, you can monitor and make sure it's on. And if you see that it's not because there's collisions, you can activate it after the fact. I showed how to use quick features. I will show more specifically in auto feature today. I think quick feature is just a version of auto feature. There's the same sort of thing. And you just have way more setting capability in the auto feature window. And it's not as intuitive as quick features. So you kind of have to search through it to look for the thing that you want to change. But the quick feature has all of the settings we really care about for beginners. So there's your clearance, cube, and planes. I did talk about this. For auto features I've shown, the most important thing with cylinders is your ending offset. making sure you're not hitting the bottom of your hole. So you want to make sure you have enough space for your probe tip, plus a little bit of a gap below that. So if we have a 4mm probe tip, there's a 2mm radius, and you need to be at least a millimeter away from the bottom of the hole. So that would be an end offset of 3mm. Feature planes. So these essentially auto feature planes and smart feature or quick feature is all going to pull up auto feature, and I will show this in the software today, and the auto cylinder I will also show in the software. And then we spent the rest of the time on the lab. So we basically covered everything last week except for the auto features that I wanted to specifically get into. Just a little more detail, that's all. Who showed up a little late that I missed here? Amal, are you here? So, Digant,
Sir Anmol present.
Amal, there you are. Okay.
Sir Abdul Moeed.
I think I got you.
Mohammed Abdul
Sir
Moeed, sir.
Mubashir.
Oh, there you are. Okay.
Sir Mubashir.
Sir Om present.
Okay.
Sir Mubashir
Missing
Alam.
you. Mubashir. I got you.
Jasim.
So if you can take a look at my screen and you see, so Digant is not here, right? I know there's two screens of names now. Digant, Mujahid Hussain.
Yes, sir, present.
You are, they are. And Ronit. Don't see you. And Samarth. Sunny. Did I miss anyone there? No, okay.
Sir
I'll take
Sohail.
that. So now I have
Sir
you.
Sohail.
I
Yeah.
have you. Oh, no, I don't. Thanks. Okay. So I hit back and it brought me there, so I might as well recover it while I was there. All right, so week 11, we have our VPN clients installed. If you have it installed and you don't know if you're connected, you should have it in the bottom right-hand corner of your main screen, and you can just see the little key, Ivanti Secure Access Client. It'll say not connected or connected. It's on the wrong screen for me to be able to show you that. But it's on your Windows toolbar at the bottom. Over by the sound and the microphone and your Wi-Fi connection. Or you can simply go in your search and type in Ivanti. Click it, and then make sure you, when this pops up, you hit connect. Once that's connected, you should be able to open your software as per usual. It won't be anything different than as if we were actually in the classroom. Our PowerPoint this week, you already downloaded this. Week 11. We added probe angles last week, so we had tool changes as well. That was something I didn't talk about. And I did show how to add tool changes with auto wrist, but that's another thing that's in auto settings that I'll show even greater. So this week, we're really going to get into kind of culminating the capabilities of this software. And the main thing we have not done yet is actually use our drawing, which can you all see that drawing I dragged onto the screen?
Yes, sir.
Perfect.
Yes,
So
sir.
this is our drawing that we have and we've been looking at throughout the class. We have datums. What we've done with these datums so far, sorry, I keep hitting the laptop, is we've basically created geometries that represent these datums. Then we've taken that programmed coordinate and we've gone to a machine and we've picked up the real life, where's the physical actual part exist in the coordinate space. When we do that, all it really is a cylinder. If like for D, for example, or E, all that the software sees is a cylinder. It doesn't know anything more than it's a cylinder and you gave it a name. Those names limit the software's capability to recognize it as a datum D. So what we actually need to do in the software to properly measure geometric tolerances and to compare drawings is to give them datum labels through the software, not just the name. So we're going to do datum labeling. We're going to do dimensioning. We're going to do constructed features all today, which seems like a lot. And I was going to start from the previous lab. I think we have enough time. I think we should just start from scratch again, just so we go through that process again. It should take us 15 minutes to get to where we got to last week, and that's it. So when we redo that, it just gives us, okay, that's the step, that's the next step, that's the next step. And the more we repeat that, the more we practice that, the more likely we are to remember. So we'll get to the point where we last week did what, a DCC alignment. That was where our lab was, right? We needed a DCC alignment, and we did various alignments. Our alignments that we discussed were based off of our feature control frames on our drawing. Like this one here would have to be an ADB alignment. This one here would have to be a CBA alignment, and this one here would have to be a BAC alignment. So now we're going to apply everything we've learned to be able to physically compare the real part that's on a machine, or at least program it ready to do the comparison. So we want to know, is that real part that's been manufactured compliant to this engineering drawing and all of these tolerances that are on this drawing? Now, obviously, that's the intention of a CMM machine. Other than reverse engineering, it's to verify that a part is compliant to engineering specs. Make sense?
Yes, sir.
Guys, don't be afraid to turn your cameras on. I know what you all look like. You should know what you all look like. Okay, so if we have to build something that doesn't exist, essentially that's a fabricated feature. It's like we're building parts, we're building metalwork, and we're making something. But what if we have something like a center line? A center line is a hypothetical line that doesn't physically have anything measurable, right? It's just something we know exists, and it's all theoretical. So somewhere between these two surfaces is the center. That center is mathematical in reality. So sometimes to build those things, we need those for drawing purposes, and I'll show you a couple on the drawing. On sheet 2, in section B3 here, we see we have a dimension 25 millimeters. Now, who can tell me what the 25 millimeter tolerance is for that measurement? So that's just a global tolerance or a global dimension, but what is the tolerance for that 25 mil right here?
0.4 plus or minus.
Yeah, 0.4, exactly. So that tolerance comes from our title block. Every dimension on this drawing with no decimals is a plus or minus 0.4 unless otherwise specified, as stated right there. So we know that that's 25 millimeters from the top surface, so from datum A to the center line of that feature. But that center line, you can't measure with a probe, right? There's nothing to contact when you do that, is there?
No.
Right. So we don't have our red probe tip can't physically contact a center line that's theoretical and doesn't exist. So to do that, we have to build the two surfaces that are on either side of it and then construct the actual center line. Then we can go from that center line to datum A and compare the tolerance or the dimensions to 25 with a tolerance of 0.4 plus or minus. So that's where we're going to get today, okay? And we'll try to do that with as many examples as possible. Because as you can see, this drawing has an awful lot of dimensions with tolerances. So there's quite a bit of work here to dimension, inspect, and program this entire component, this entire part, which we won't be able to do because it's quite a bit of work. There's 6 sheets of dimensions. So we're gonna stick with sheet 2 for now, but for Samarth, you have a question?
Yes, sir. Yes, sir. Uh, Actually, I just want to inform that I am present, but my mic was not working. So I just put it in the chat that I am present.
Okay. You're saying your microphone wasn't working?
Yes, sir.
Is that what you said? Okay. I think I didn't have you mark this here, so I'm going to try and do this in a new window just so I have it available. I don't want to keep getting distracted finishing attendance, so I'm going to probably leave it for now. Yes, okay, I got you here. I'm missing Rolnit, Sunny, and the guns.
Okay, sir.
Good turnout for the quick change. I just changed it at 10:30, so I appreciate everyone making it. I know it might actually be quite a bit easier for you to make it to online than in person, but these are hard concepts to teach when we don't have a physical part to talk about and a machine to talk about with it in person. So at this point, what we're doing today, I knew I could easily move it to online, so I wasn't too worried about it. Okay, I was talking about center lines. We're building center lines. So we have to learn how to make what in the software is called a constructed feature. So building from lab 3, let's start that over again and reconstruct lab 3. Okay. So we're going to open our software. Who's able to do this? Show of hands, who's able to get in our software now with a VPN client? Some in chats. Okay, a couple thumbs up. Ronald, okay, this is good. So this also should allow you to practice this at home when you can't get to campus or something like that, you can practice. We are limited on our number of licenses, so to I think 60. So if there was 30 people on to record this meeting locally, I am going to deny your request to record it because I am also recording, okay? Sahil?
Okay, sir.
Yes, it is recording. So I will share a recording with you all, okay? That way it works a little bit different and then I can have an expiry date on it and stuff like that. So we're good. We're going to create a new routine. This time we're going to start, instead of building on lab 3, we're going to build our week 12 routine from scratch because I want to practice everything all over again. We're going to keep our millimeter unit and we're going to be offline, obviously, because we have no machine connected. That already exists on my computer because I started this. I'm going to overwrite it and start from scratch. As we discovered, we cancel this, and we're canceling it because our one sensor is broken on our one machine, and nothing we're doing at this point is critical enough. If you ever needed to, you could go in and you can add this into your routine, and you can reactivate it even if you've canceled it. But we're going to cancel our temperature compensation. I want to see probe files 4x50SF, and you guys got to kind of see why that mattered. A few of you did last week when you ran lab 3. If your file looked like anything else other than 4x50SF, when you put it into the machine, the actual load probe ended up red, or the tip angle ended up red. And that was because that probe file didn't exist on in the software of the machine. So this is the probe file that's used on all our machines in the classroom. So the tip only exists under that probe file. So if you saw this as red, you had to go in and change the probe file when you loaded your program onto the machine. Now what do I do? Someone, what do I do next? What's my next step?
Load the
Import the CAD file.
Import the CAD file. To do that, I go to my CAD toolbar. And I go import from CAD. you want to make sure this filter is set to IGES so that you can see your IGS files or in your IGES files, but in this case, they're IGS. So hex mi underscore demo block small, you double click. I'm going to zoom out a little bit with scrolling my mouse. I'm going to rotate it by holding the scroll, and I can right click on my mouse to drag it around a little bit. I'm going to fix these surface vectors, graphics display window, CAD vectors, and I want to fix the surface vectors. Now I'm going to program an ABC alignment. ABC is the simplest form of a 2D alignment. And what it does is it gets your coordinate from your machine axis, from your machine coordinates to your part. It identifies an origin on the part. And in this example, it should match this CAD origin exactly, because it would be, Z would be constrained by A, B is going to constrain your Y, and C should constrain the X. So we know that the origin should be in this corner up here. Okay, so we're going to do a two-dimensional alignment. Who remembers why we do two-dimensional alignments, 2D alignments when we're in manual? Why would we just not go plane, plane, plane? And why would we go plane, line, point? What's the difference?
I think because the origin is somewhere in the in space, so
Yeah.
somewhat you have to bring it down to the
Right. So that's the point of an alignment. But what if we could just do a plane, plane, plane alignment? A 3, 3, 3 points. And we could do it that way. Or we can do 3 points, 2 points, and 1 point. Right. I can't monitor the chat necessarily at the same time, but Arif, yes, that's right. So save time. So we could save time by and operator inconvenience and potential errors by doing a 2D alignment. Yes, it does cost a little bit more time in programming. It's worth it in the long run. All right, so the first step to do that is you always want to, in manual mode, you want to tell, sorry, I got hiccups. You want to tell the operator what to be doing. So we must use comments.
Comments.
Right. So we did this in our lab. There's a requirement to have your comments. So we're going to insert a comment from our comment toolbar here. We're first going to make our A. Our A features primary, so it has to be 3-dimensional. And then the other objects can be 2-dimensional after that, as long as they constrain 6 degrees of freedom. So we have a, please take 3 points on the top surface. Okay. And then to do that, how do we create those 3 points? Not working. What did I miss?
Programming mode.
Correct. So drop down your probe modes and you go to programming mode or program mode. Now you can pick your 3 points. Make sure your red arrows are correct, normal to your points, because that's your tip compensation for each point. And you click end. I now have my plane 1. When I do a 2-dimensional alignment, my line has a dependency on the previous 3-dimensional feature. This is about how probe tip compensation is going to work, because in our CAD model, everything looks perfect, but in real life, our part's not perfect and our planes might not be perpendicular to one another, or it might not be aligned to our axis perfectly on our machine. So if we do not first level our plane, our 3-dimensional feature, with an alignment, then our line that we build, or a 2-dimensional feature we build off of it or after it, will have the cosine error on the compensation. So we want to make sure that plane, it's a long way of saying, make sure you now do an alignment on your plane for a level. So we're going to do our auto align on our plane, and we'll just leave the name as A1. We're going to click OK. And now we can build our line. But we have to have that leveled alignment before we can build our two-dimensional line. This only applies in manual alignments. Once you have an alignment done, you can build two-dimensional features without cosine because you've now compensated for all of those errors. Sorry, without cosine error. So now we're going to take our 2 points. What should I say here?
Please take
Hmm.
2 points from right to left on front.
Yeah, okay, right to left on the front surface. I like from right to left just because of the way I run the machine. I like to take my point here, 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 and then here and here, and it's the shortest path. But this part I know, I run this part a lot, so it might not be as obvious or as intuitive on the first time you look at a new part. And then we could program the same way we told our comment to do. Right to left, because that makes a vector pointing in y minus direction. If we did left to right, this is just a demonstration, our vector is the other way. And that is important that we do it the correct way. So I'm just going to delete that extra line I put in there. Maybe. Delete button's not working. There we go. And finally, so we've done our 3 degrees of freedom here. Our line is now something we align before we do our points. Now we do our line, auto align, watch your triad, and then you can see it's only open on the X, which means we don't have our 6 degrees of freedom yet. We've only got 5 constrained. So now we build our point. Please take 1 point on DMC, or you could say on the left side because DMC is the left side, right? And 1 point here, click end, and finish your alignment. Your point, auto align, verify your origins in the correct spot. This makes sense, not the point, but the origin. And it's constrained. There's no movement on your triad, that it's all, and then you can be ensured that your A3 alignment is finished constraining your 6 degrees of freedom. You click OK. Now I'm going to do this just because I don't like looking at these extra labels. I like to hide them. So I click the eyeball, show hide, and I never will look at my manual features ever again in this program. I've created a plane there just to give an approximate location of the top of my part. I've created a line to create the rotation of that part on the machine and a point to show where my X is. I really don't need those features ever again in this program because they are not a good representation of that surface. So they're hidden now. They still exist. The alignment's still done. I just don't see them on my graphics display window. Now, I also like at this point to turn off my program mode because I like to do everything else in my quick feature, my auto feature tool. It's optional. It depends what you prefer to do, but this is my preferred and I think the easier way for students to learn. Okay, so I've done my A3. If I'm going to go into start measuring features in auto feature, the first thing I got to do is make a new alignment. I'm going to make an alignment based off of my drawing. So if my drawing looks like this, it doesn't immediately tell me, but how about that 10 millimeters or this 25 millimeters or this 30 millimeters? How do I know what alignment to use when I'm trying to measure 25 millimeters, 10 millimeters, or 30? Anyone want to take a guess at that?
Sir, can you repeat the question?
So I need to do an alignment now. So I've done my manual alignment. It's just an approximate location of the datums, right? It gives me, okay, here's my machine coordinates. Now here's roughly where they are in the part because I've done a manual alignment. I've always repeated my manual alignment with a DCC alignment, but I've never really discussed with you which alignment you choose to do first. like my goal ultimately is to take this drawing and to measure the 25 millimeters, the 10 millimeters, the 30 millimeters, the 40 millimeters, the 35 millimeters. So I need to verify that these values, all these values on this drawing are correct. But I don't know where to start. And I could check this and I could say, okay, if I start with inspecting this whole pattern, I need to start with an A. Well, I don't know how I bolded everything there. I need to start with an ADB alignment. So it depends which thing you choose to inspect first on your drawing. Okay, as to what alignment you're going to choose to do in DCC. Now, 10 millimeters, where is the origin point of that 10 millimeters? Datum B, right?
At datum B. Okay, sir.
Right. So if datum B is our origin, or actually it's kind of datum A, B, and C, if you think about it's on this corner, then it's logical to think that, okay, an A, B, C alignment is probably a good starting point for this tolerance, this tolerance, this tolerance, this tolerance, this tolerance, and many others, right? So we can probably do an awful lot of inspection with an ABC alignment. And it's what we did in our manual. So I'm going to suggest, based off of that, that we start with an ABC alignment and inspect everything we can on our drawing with that alignment. Am I making sense? At least a little?
Yes.
Nope. All right. So we're going to do that. We're going to do a DCC ABC alignment. So what do I do first? This is part of our lab, so everyone should know the answer.
On top left near the programming mode.
So on top left, we do programming mode. Is that what you said? If we're going to build our features, A, B, and C in DCC, we're going to use the auto feature or the quick feature, right? If I do that and I hold shift and I click here, I get this 0 out of 3 feature. It's not actually the right setting.
Shift and then click on the surface.
So I did that. I did shift and I clicked on it. But the problem is I'm not in DCC mode yet.
You have to activate.
So
it.
if you see this happen ever when you're building a feature and you don't see the proper, actually it works on a cylinder, which is interesting. If you don't see the proper information come up on a plane, then you know you've forgotten to enter DCC mode. Yep, there we go. Sahil. The clearance cube needs to be turned on. Now we're on the right track. So we go to our clearance cube toolbar. We turn on it. We activate our clearance cube. Your clearance cube settings window should pop up. And if you look on your toolbar, it's blue. The clearance, activate clearance cube motions. Then what do we do?
Activate DCC mode.
Activate DCC mode. So there's something I need to do before activating DCC though. That's the next step, but there's one important thing before then.
Command.
Comment.
Comment. Yeah, what's my comment I have to do? I have to say.
Make the probe outside of the clearance cube. Move the probe.
Yeah, so that's kind of the right, but make sure your sentence is nice and clear and you want them to move the tip above the clearance cube. So the operator needs to physically take the joystick in manual mode and move the tip up above the clearance cube before anything activated, before any DCC movements, okay? So please move the tip above, above the clearance cube. And then I say DCC is about to start. When they click OK, it activates DCC mode. because the next command after the comment, forget who said activate DCC mode, but now we can activate our DCC mode. So it goes to comment. As soon as you clear the comment, it moves to the next line of code, which is DCC mode. Then from DCC mode, it starts doing everything automatically. So we're going to build our A, B, and C now. Build our A, shift, click. Now that we have something that's a little more representative of a good surface A, meaning there's 9 points on this, we could change this. Just for fun, let's make it 25 points. Number of hits per row is 5. Number of rows is 5. If I instruct you to change these settings, you must change these settings. It shows me you're paying attention and you've actually read what's in here and not just hit OK. So 5 hits per row, 5 rows, which is 25 points. We are going to use our boundary offset and our void detection, and we're going to make our boundary offset 2 millimeters. Just in case there's big chamfers or something on the real part. If let's say it was 0.5 millimeters, my points are right on the edges there. You can tell that I'm so close to the edge. If there's any kind of filed edge there, I'm going to hit on the filed edge and not on the plane. Even 1 millimeter is still risky. It's probably okay, but 2 is going to be safe on almost everything you do. That's why I chose 2, is monitoring those points, the distance they are from the boundary of the voids. Holes are voids, cutouts are voids. Any feature that is not on the plane is a void. Okay, so we're going to click OK. Now I want to show you auto features really quickly, because I talked about it last week and I never got to doing this. I double click on the feature. I have multi-screen, so it popped up on the wrong screen. Double clicking on this, my auto feature window comes up. This is a lot of the same stuff that's in quick feature, because they are the same tool essentially in the software. This tells you the theoretical center point of the measured feature. A plane has like a weighted average center point because there's a whole bunch of points. Mathematically, they have to pick something, and it's going to be weighted based off of mathematical center. The surface is the surface vector, and the angle is it should be the, pardon?
Sorry, sir.
Did you have a question? Just interrupt me if you guys have questions, okay? Please. I might not see your hand up, or I might not see the comment or the chat. So the angle will be the tool's angle, the way that the tip angle of the shank is actually approaching. Now, if you see this and you don't see more settings underneath it, you click Show Advanced Measuring Options, and you can change a lot of features here. My favorite settings to change are the little anchor. I like to see this one on auto wrist, which means it's going to automatically pick your tool angle that's appropriate for that feature. There's times where you don't want that and you override it. Like if I tried to measure this plane here, it's going to make me change the tip angle, which I don't think is necessary. And then you can have clearance moves, which is something I don't need to teach you about right now. I can have show hit targets, which completely hides the tool path. I do want to see that, so I'm going to leave it shown. I have 2 that I'm not going to show you again, how to view them, and then void detection. I can turn it on or off, just like I could before, but I want to use it every single time, so we're going to leave it on. And then you have show measured points, which actually just create the probe tip looking points. They're not really necessary, but they might be helpful for just as a visual aid. I like these on measurement reports, so I got these from customers that inspected for me. They'd send me the hit target points on each datum, so I knew where all the points were taken on the part, and I understood the results based off of those. If I wanted to repeat it, I knew where to hit. And that kind of shows the top bar here. Then we have the lower bar here. We're not going to change the math. I talked a bit about how the math works, whether you're using the average, you're using the max and the min. But we're going to leave it for now because it's a bit more of an advanced CMM setting. We'll start at the right-hand side, contact find hole properties. Well, find holes, guess what? It only exists on holes, so cylinders. It's not something that exists on a plane. Contact auto properties. This is your before and after. Basically, are you going to avoid something before coming to your hit? Or where does your rapid movement stop and your contact movement start? If I made this longer or higher, a larger number, you can kind of see. If I just have to click on there to update, there's my before and after movement. It's gotten longer. Oopsies. I just changed the name. The top is your name, obviously. So if I change this back to 10, I did it again. And 10, it updates my before and after avoidance. This is more important in features like I'm pointing at my screen, like that's helpful. The before and after is very helpful when you're into a feature like this one that's blue now on my screen on the front, because you need to actually be outside of there to not hit the center stubble that you're seeing in blue. See, there's something that's a lot more useful when you're in person. I could point to that a little easier. Okay, so moving to the next, contact sample hits. We don't need sample hits on a plane. Sample hits are more for circles, and they help you find the center of the circle. Hits per row, rows. Well, we adjusted that to 5 and 5, so we could change that now if we wanted to modify it. We do not need the feature locator. This shows you the theoretical points. So where are all the hit targets? And you can kind of go through each one. You could modify these. I don't remember. Oh, you have to drag them. So you could drag it and you can modify it. I prefer not to do that when possible, because then you're modifying the algorithm. And the strategy that's used, we can make our own strategies in the measurement strategy editor that I've been trying to figure out this tool here, why for half of you last week it was unable to save the settings changes. So when we tried to make our own defaults, it didn't work. I don't have a full answer yet, but it has something to do with the default save location. So there's something funny about how some of you installed the software. Maybe you changed the default directory, or you have some sort of write protection on your directory. Haven't solved it yet, but trying to figure it out. And I think that covers everything in our what's this one? Position probe. So that one's kind of unimportant. I have somehow turned off my void detection though. See how it went back to the grid? If I went and I looked at my grid, the spacer would have to be increased to change the grid size. But now the grid is half touching air and not touching the part. That's why I like void detection. It's so much more powerful with void detection turned on. I do not expect you to memorize these icons. They're kind of ridiculous. They're not intuitive at all. I just want you to know you can find them by searching through. You can find it at the settings that we talked about with quick feature. Was that a lot? Probably. We'll finish our A, B, C alignment, and then I'll give you guys a quick break, okay? All right, so we're gonna do our B plane now. Who remembers how to make both surfaces yellow? How do you give the last offset? What do you mean by that, Sahil?
The click shift and click both on the and drag the mouse.
That's right, Jacob. Good job. So yellow and yellow while dragging the mouse. It has to be clicked down while you're doing that. I'm trying to still address Sahil's question because I'm not sure what you mean. So in auto feature, okay, so let's just open plane B in auto feature. I'm going to just hit OK, and I forgot to change a few things. So I'll double click. My boundary offset was one of the things I did not change. It opens as the default. The spacer I'm going to leave alone. This one I want to make 5 rows of 5. I changed my name by accident. PLNP. Which one do you mean the offset? How to give the last offset? I'm not sure which one you mean in the auto feature. Can you turn your mic on, Sahil? Or
Sir, in the online mode, you did the offset. You just corrected us while giving the lab 3. The last figure that the offset you changed, we got stuck there.
can you show
Offset.
me?
So he's talking about
you-
that
ADB
tool
alignment,
was
is he talking
crashing.
about ADB?
Okay,
The
an
tool was
ADB.
crashing. Yeah, the tool was crashing inside the cylinder, right, sir? The offset
Oh,
you
yes.
increase the
I can
offset.
show
Yeah.
that, but I need to finish the ABC alignment first. It was the before and after that we can change that with the avoidance. So if you change the avoidance distance before and after, you can fix that. But I'll show that after. Okay, let's finish the ABC and the alignment, and then we'll start building the other features to inspect our drawing. I'll show you the constructed features and the dimensioning. Okay. We're going to click OK because all I changed is the number of hits and the number of rows and the boundary offset, which are things I can change when I'm in quick feature. I just have to remember to do it. Like here, I need to make that 2. I need to make that 5. I need to make that 5. Well, not 53. That makes an awful lot of points. If you do too many points, it's going to take way too long to run on the machine, and we just don't have the time. Our plane was on plane C. And I did the same thing. I held shift, I held my mouse down, and I dragged while holding the mouse button, the left mouse button down on all 4 surfaces, and I identified those 4 pads as one continuous feature. Click OK. So auto feature for the planes is always going to be the same. I have an A, B, C alignment. I'm going to finish my alignment from a new alignment. Because this is a 3-dimensional alignment, 3D, I can do it A, B, C all at the same time. I would like you to always name your DCC alignments appropriately so that you know in your routine, and you'll start to see this when you're dimensioning and we look at the report window, why it makes more sense. A, B, C, you select in the order of datum precedence. A is your primary, B is your secondary, and C is your tertiary. The recall should be startup because we're starting over again. Make sure that triad's floating. So we don't want any dependencies on any other alignment. We just want to start from the beginning. And that right there, if I hit auto align, watch my triad, it should be where? Based off of A, B, C. It should be in the top left front corner. Right there. And not moving. I know 6 degrees of freedom are constrained. My origin's in the right place. The Y is pointing in the correct direction. The X is the right direction. The Z correct right direction. And if you're not sure of those things, you should still be using the old version where we manually select A as our Z plus level and then our origin, so that basically you're following the steps and you understand the steps as they happen. Auto alignment does not always work. Sorry?
So can you please repeat the ABC alignment?
Yep, I'm going to delete mine, okay? So I deleted that line in the code. I go to new alignment.
Yes, sir.
I make my name ABC.
Yes,
I
sir.
recall startup, so my triad's moving. And now I know A is my primary datum because it comes first in ABC, right? B is my secondary and C is my tertiary, or
Yes, sir.
third. So you click them in the order. You get a 1, you get a 2, and you get a 3. You
Yeah.
do not want to use your manual features to point the line in the plane. Those are stuff that we're not going to look at anymore. That's why I hid them. They still show up here as features, but they're not things we ever want to use again.
Yes, sir.
And this is now going to refine the origin on that part. It was close to perfect, and now it will be perfect. That's essentially what you're doing when you click auto align. Now it'll be perfect when you run that. You click OK.
All right, sir. Thank you.
Okay, I'm going to pause the recording now. We'll have a break and we'll be back in 10 minutes. So let's do 4:05 and I'll see you guys then. How to verify the degree of freedom that's constrained. So Sahil, before we go break, I'll answer that question. When you click your ABC alignment, like how do you know which is constraining which? The best version is when you're in the alignment window here, or the alignment utilities window. Your triad's not moving. And if it's not moving, then you know 6 degrees of freedom are constrained. You don't necessarily know the correct ones because you don't know if it's in the right place. So you have to think about your datum precedence. You have to understand datum precedence. And maybe if you don't understand it, complete the datum precedence table, because then you at least understand the origin should be constrained by this origin should be constraining this origin is this, or this axis is this. In this example, A is constraining Z, B is constraining the Y, and C is constraining the X. So we know that triad is in the correct corner. That help? And then if we, for example, we deleted the X plus translate, if I delete that, my triad's moving. And I can see it's not constraining 6 degrees of freedom, but because it's moving left to right, I know it doesn't have an X. If I looked at my datum precedence table, I would know plane C constrains my X origin, and I've now constrained it. So it's all about understanding what happened on that datum precedence table, whether we have it or we're not. What if they were over constrained? If you tried to over constrain something, like I will show an example of that really quickly. Here's my D. I'm not going to label these. Here's my F. And so if I asked you to do a DFA alignment, it would look something like this. It would be D, which was cylinder 1, F was cylinder 2, and A is tertiary. Right? So this is theoretically an alignment that you could be asked to do. If I auto align, it gives me an error. And it's saying plane A is not used. So all the degrees of freedom are already constrained by the 2. So it knows that D and F would fully constrain a feature. So it's actually just DF that's needed and A is redundant. If not all 5 are constrained, it doesn't necessarily warn you that. It's just that the triad's still going to be moving. If it's over constrained, it tells you though. Okay?
Yes, sir.
All right, let's take our break now. 7 minutes after 4 now. And I'm pausing video. Okay, welcome back. All right,
Yes, sir.
so our ABC alignment is done. Now, this is as far as we've really gotten so far. And we can do this theoretically in 15 minutes. If we do it a lot quicker, we could even do it quicker than that. Now, what we want to do is we want to inspect criteria in the drawing. There was a couple other requests during break there. Like how do we do a cylinder and avoid the collision that we saw last week? I will show that one quickly just so you guys also, Digant has a question. Let me finish this and then I will get to your question. So if I show auto cylinder, then I can use the auto cylinder window to show you how to fix that issue from last week. Digant, you put your hand down. Does that mean that this was your question? How to do this?
No, sir, by mistake.
Oh, okay. All right. So when we do auto cylinders or quick cylinders, that yellow feature, I call it quick cylinder. We want to make sure we don't select near the bottom, like where my mouse is. We want to select close to the outside here. What that does is it allows us to ensure we get the appropriate. Now I get this warning that comes up auto wrist. That's because I enabled auto wrist. You may not get that. So technically we should think about this before I did that. Okay, does that tool angle work for that feature? No, it does not. We need to be pointing towards that feature, which means we need to be an A90 and we need to flip all the way around at 180 degrees. So to do that, we showed you how to insert a tool change from the settings. As long as you have that tool built in your profile or that tip built in your profile, it'll change the tip angle of the probe. That's one way to do it, or you can use the auto wrist, which if it's enabled, but that should not be enabled yet on your auto feature. Now I'm going to click near the outer part to ensure that my end offset and my depth do not get reversed. Okay, so I have all my points in a quarter of that cylinder. I don't like that, and I think that's way too many points to begin with. So I'm going to change this to 5 hits per level, and I'm going to change it to 2 levels. That isn't always what you want to do. If you have large cylinders or really deep cylinders, you want a lot of levels. I just think doing 5 levels in that short of a cylinder is a bit of a waste of time, especially when in our classroom. I would consider the precision of the hole requirement, or the precision on the drawing for that before building that feature and the point density. A higher precision requirement, I would have more precise or more points or a higher point density in that feature. Okay, now our end offset is it should control the bottom layer. It should move away from the bottom of the hole. If it's not doing that, and you can't really see when you're in when you have 5 rows, you can't see that. So when you have 2 rows, it's pretty clear to see. When I change this value, my end offset, to something like 3, which one changed? If it's not obvious, change it to 5. That's changing the bottom. That's what I want it to change. If that's not appropriately changing it and it's moving the top, then you've actually selected too close to the center or too deep in the feature, and your depth is now going to control your end offset, and your end offset controls your depth. So just a weird glitch, or I don't know what it is. It's just the way the software is made, and that should do a pretty decent job. If you want to move in on a helix as you come down, you have to enter a pitch, and it's just basically going to create it like a screw, and that is how you would inspect a thread. You'd follow the pitch of the required thread. I'm going to keep it at 0. Now, I can't change something I want to change here, which is this should be 360 degrees. I should be measuring all the way around there. So here I will get to your question. Now, so to fix that, I can call this something correctly, like front outer cylinder, something like that, or that in the future, it makes sense to me what that is, because cylinder 1 might not be clear. I'm going to click OK. Now I've got this feature, front outer cylinder, but I didn't like where the points were. See, when I double click, I open the auto feature version, and I have more information. I have an orange arrow and a purple arrow, which are actually the start angle and the end angle. For example, if you're doing a half a circle, you're going to want to have a start angle and an end angle. You're not going to look for points all the way around a hole that doesn't exist all the way around. So we're actually just going to change your start angle to 0, our end angle to 360. This didn't take. And by doing that, I've changed my starting and my end points for my point. It doesn't have to go all the way around because there's a wasted tool path here. It just goes this way, then down, and then back the other way. Or down and then out. It should actually start at the lower level. Now, this is the issue we had last week. This line, we can see it runs right through the stud of this part. So in this auto feature window, everything else is pretty much the same. Turn on auto wrist. This is all the exact same information as the last I showed before. This is pretty much all the same, except we have this find hole, which will give you an option if there's a hole drilled in a very wrong location. It's often used on a real life part, especially if it was done on a manual machine, because there's not a good they're not highly repetitive like a CNC machine. So you will often use that. It just takes more time to run the part. So what we're doing here is it's that avoidance move. So is it avoiding something before or after? How is it doing it? let's play with it a little bit. Let's say if there's no avoidance move, what happens? It actually starts inside the feature here. Both. It's starting 10 mil away and ending 10 mil away from the center of that feature. If we said before, well, if there's only one direction, it starts before, then it ends inside the feature. How about after? It starts here and it ends here. It's still potentially running through that part. Usually I leave it on both because I'm not 100% sure how none works. I'd have to simulate that to check. That actually probably would work. I think if we have none on this, we wouldn't have any collisions. Just looking at the toolpath. But let's say we click both. If we want to avoid that, we just need to start farther away to change the arc. And I'm changing the name of this feature here. My numlock is kind of doing some funny things. Okay, so let's say I started 35 millimeters away and ended 35 millimeters away. You can see the toolpath change quite substantially, and now it's kind of looks like it's avoiding that center stub. So that's all it takes to avoid that collision that we were seeing last week. Is it's going to come here for the based off of the clearance cube. It's going to move away from the clearance cube, and then it's going to approach from that 35 millimeter, and then it's going to finish at the 35 millimeter distance. So I hope that helps clear up how that auto feature works for cylinders and how we could have avoided that collision in that example I gave last week.
Sir, how are you simulating it? Like how?
I will simulate it in as a collision detection. So I can undo this at any time and I can see my collision detection.
All right.
So just like so. So I have a lot of planes in here, so it's taken a long time because I did 25 on every plane.
Oh.
And there, it says I'm clear. So I didn't get the collision this time. If all I change is my avoidance moves, let's say this is 10 again, and I leave it at my default. When I simulate it, I should have a collision there. I'm only going to simulate the one feature. I have a collision right here. It's actually not showing it in the right location, but between plane C and that feature, there's a collision, and it's coming from right there. That's how you kind of troubleshoot things, and you realize, oh, I can fix that collision by tweaking something, then you should do it. Now, I don't want this cylinder right now. I'm going to delete it. I just wanted to show you how auto feature worked for cylinders and how you can use avoidance moves to help avoid that center stub. I'm going to also delete that tool change because I want to look at my drawing. I want to start inspecting my drawing. Okay, so I am a customer, or you have a customer that says, hey, can you inspect this sheet for me? Let's say it's only this sheet. You're going to get a PDF drawing, or you're going to get a paper drawing from the customer that looks like this. You're also going to get a part that looks like the one on our machine. This is understandable, right? Makes sense. What we're going to do to make our lives easier and their life easier is we're going to take that drawing and we're going to start identifying which dimensions are on this. For example, 1, and we put a little circle around it. Now, there's a better tool for this, and there's a stamp in here, the dynamic stamp that I used to have functioning, but I don't know how to make the script anymore, so I don't know how to make a circle with a number in it that changes every time you click it. I've forgotten how to do it, but it's much cleaner than what I'm doing here. And then you say, okay, that 35 millimeter can be number 2. This 15 millimeter tolerance can be number 3. The 60 millimeter can be 4. And ultimately, every single one of these dimensions needs to be accounted by a number. This flatness is going to be 1, 6. It's nice if you can go around a drawing like this in an order that makes it fairly easy for you to find the numbers later. 8. And these are called balloons, or this is called ballooning a drawing because they look like a balloon, I guess. And then you have a number. So this is messy because I'm doing it with a with a mouse and a draw function in here, but normally it looks nice and clean. So you're going to return this drawing ballooned to your customer. But that doesn't answer everything, okay? So I currently have a few on here, and we're going to cover just a couple of these I want to actually answer because we don't have time to do them all. I'm going to do 9 here, and I'm going to skip a bunch. 9 here. I'm going to do 10 on 10 and 11 on 5. So let's cover, for this class, I'm going to have us try to complete 1. That's a bad color choice. We're going to go with number 1. We're going to go with number 8. We'll go with 9, 10, 9, 10, and 11 as well. So we're going to try and complete those dimensions and program those to actually complete those features. All right. Okay. So let's look at number 1 first. We need to build a dimension for number 1. So we need to compare this edge, C, we know that's C, to 40 millimeters to the center position of this hole. It's never obvious to me when there's 3 concentric cylinders, which cylinder it is you're supposed to inspect to. But I'm going to choose the cylinder on the smallest diameter. And I'm going to say, is that smallest diameter 40 millimeters from datum C? So how would we do that? Well, we actually have to build that cylinder or circle and the datum C. Now, we know we've already done datum C, haven't we? When we did this alignment, we already built and programmed datum C. So it's not something we have to do again. But what we don't have is any information on this hole location. So what I ask is, does this, to get a position from here to here, do we need this to be a cylinder or can it simply be a circle? All we're looking for is distance.
Circle.
Circle's perfectly fine. Absolutely. Now, so to do that, we're going to, for the first time ever, we're going to use shift and we're going to build it as a circle. Now, there's a weird thing in IGES where it breaks circles apart and makes them half circles or quarter circles, but we can solve this problem. So it's only identifying a quarter of that circle. Shift, create circle 1. Circle 1 is actually circle F, I believe, because that is the datum F on the drawing. I can take a quick look at that and say, where's datum F? Because I think that's true. Right here, right there. So you could actually get more creative here. That hole that we're measuring to has also a diameter tolerance and a true positional tolerance. We could measure this at the same time as this by building it as a cylinder, but I don't want to get that complicated yet. We're just going to go with the circle for now. I'll show you why you might use circles sometimes, but understanding that that feature is the same feature as this feature is sort of important to recognize. So studying your drawing is a good start on how to program correctly. Back here, let's build this circle, circle F, and we know it's called F because of that name right here. Oh, it's E, sorry. It's not F, it's E. Is that what you're going to tell me?
No, so just doubt. So what about the you just did the angle change and did a cylinder, right? So do we have to delete it before doing it?
Yeah, I used, and I actually, you made me notice that I had my cursor in the wrong location as well. So
Okay.
stick with your A0, B0, all that stuff I just showed you, delete it. It was just to practice that tool.
Okay.
We can build it again later if we want.
So we'll be doing it after the ABC alignment, right?
Everything, yeah. So everything you're going to program and inspect
Okay.
is after your ABC. anything that's relevant to ABC. You can't then check your ADB features until you've done an ADB alignment.
Okay. Okay.
So let's build this guy, the circle. It's circle E. Let's change your settings. The number of hits is 6 is probably fine. The depth is important on a circle because there's only a depth. It's one level of circle of points. So what depth are you taking those hits at? 2 millimeters should be fine on a 4 millimeter tip. We're going to click the check mark. I'm going to double click to change my start and end angles. So see how I'm constrained to 90 degrees here? I'm going to change that to 360 degrees. So my start angle is 0. My end angle is 360. Oops, not 350, 360. Now all my points are spread evenly around. So just the default there for some reason was 90 degrees. I don't know why exactly, but I can fix it. I wasn't too worried about it. This is an example where you might want to move your avoidance moves because you can see that I'm starting inside the part there. That could potentially be risky. But I see the green line because it's going to go from the clearance cube down to that point and then start measuring the feature. I'm okay. And then when it ends, it's going to go back to the clearance cube. If you don't have clearance cube on, this is risky. And we're going to, everything else can be default. So cylinder E, all I changed was the start and end angles here. Sorry, yeah, start and end angles. Click OK. All right, I have a circle E. Let's say I executed this program and I want to measure my balloon A, my balloon 1, sorry, up here, my balloon 1. So to do that, now what I'm going to do is identify the tolerance of my 40 millimeter. That's a nominal dimension of that feature or the nominal position of that feature, right? 40 millimeters from the edge. Well, what's my tolerance? We talked about this earlier. Plus or minus 0.4 millimeters. Okay. Now I'm going to go into my part and I'm going to create a dimension. So go to your dimension toolbar and I'm trying to identify the X position of my circle E. X relative to my C, because that's on the X axis. So what's that distance? See how this is the X on the drawing? This is X, the X axis. So that's what I'm looking for. I'm just looking for the X distance. I could go from here, I could go dimension, and then I have all my features that I've created here listed. I need to select 2 because I'm saying what's the distance between this and this? So what's the distance between my plane C and my circle? Exactly. And then you can give this a name that makes sense. Well, it's called balloon 1. Now it's really obvious that should be the same thing as our balloon on our drawing. That's that. Now, this looks a bit weird because there's a lot of options here. And it tells you the plus or minus tolerance. It gives you a default and it gives you a nominal, but that nominal doesn't make any sense because the drawing should be 40. So what's
Sir,
actually
can you-
happening? Pardon?
So can you show how you open the distance again?
Yeah. Close. So you're at the bottom. You're after the feature. If you're not after the feature, it won't see it. So if I try to do it here, circle E doesn't exist yet. So I'm after circle E. I open my the red toolbar, or it's the dimension toolbar. And we are going to use a few of these, but that is just a distance. It's an X distance between 2 features. So distance dimension. Then you select the features you're trying to dimension between cylinder plane C and circle E. We give it the tolerance based off of the drawing, which we know is 0.4 plus. And it's also minus 0.4, sorry, 0.4, not 0.04. So we have our tolerance plus and minus is correct. And our nominal is not correct. That has to be correct. Well, it's the way that the features are built. That plane had a center line or a center point, and the circle has a center point, and it's just giving you the distance between those 2 points. the center point of the plane and the center point of the circle. Well, if I said, no, I want to lock that to the x-axis, it's now going to recognize that it's all on the same level. So it's going to take the point and the plane and just look at the same level. What's the distance between here and here on the CAD model? And that's where the nominal is going to come from. If you see this and it makes sense to the drawing, that's what you need to look for. You could also often change it to 3-dimensional and it recognizes that, oh, I'm actually looking to do it like this, and I'm doing this distance, not this distance. So this is really just something that comes, you play with it until you identify what your nominal is that you're looking for correctly. Obviously, we're looking for 40 millimeters because our drawing's nominal is 40 millimeters. The CAD model and the drawing should have the same nominal. The part won't have the same actual value, but it has the same nominal, meaning the designed value. What's the actual value? And that is simply, like I said, I wouldn't spend a ton of time on how to do dimensioning because it's really not that hard. We go pick the 2 features. We pick the name correctly. Balloon 1, create. Now, when I click close, I could build another distance at the same time. So it's just kind of, you have to close it to change it. I have in my routine a green value. Basically, that's saying that passed, meaning it's in the specifications that you gave that value. How to generate extra angle from the probe during programming. Okay, I said I'd come back to your questions, and it's 20 minutes now, so I should probably come back to that. Let me just sidetrack on the balloon for a second, and we'll come back to it. Sahil, you said how to generate an extra angle for the probe during the programming. So what I think you're asking is, how do we insert a new angle in here? Is that correct?
Yes, sir.
Okay, so if you don't have the angle you think you're going to need in here, you have to look in your probe file, go back up to the top, double click your probe file, and you have to make sure you've added the correct angle. So when you click add on my wrong screen, I've had this pop up, add angles, and you can pick and enter your angle you need to add it to your active tip lists. When it's in your active tip list under the profile, then it's selectable under your settings toolbar. That makes sense?
Sir, can you tell me how to select that circle from
How do
cylinder?
I select that circle?
From cylinder.
So if you don't want a cylinder, when you do shift and it's yellow, the whole thing looks like a cylinder, right? I'm going to do it up a little higher so there's more space. But if I drag my mouse up, it becomes a yellow circle.
Okay, sir.
So when I do that, that's a quick circle rather than a quick cylinder. This would be a cylinder. This is a, whoops, that's a plane. This is a circle. So the difference between a circle and a cylinder is a circle is one level and a cylinder is a circle at multiple levels. How many levels you choose to do that at, or if you choose to do it in a helical pattern, is up to you. But, and one's a 3D feature and one's a 2D feature. Okay. So what I want to show now, and this doesn't show as well online, is when I click balloon 1, it doesn't tell me anything. It doesn't tell me the actual values of circle E. I don't know the actuals because I haven't run the program. All I've have is code saying, this is what I want you to do. And it's saying based off the CAD model, it's passing. Well, of course it is. The CAD model is perfect. It was the nominal. So your part's not made to the nominal. It's made to something with tolerance, some actual machining tolerance. So to visualize that and to now put everything together, we have to go to our report window. So on the top, on the quick measure toolbar here, we have the report window toolbar, second one from the end. We click on that and we're going to see our report, which, if done correctly, is relatively easy to understand. We have from our customer a drawing and a part. What we send back is their part in the same condition we got it in, and their drawing with balloons on it and an inspection report. So we sent them this. So right now, if I sent this back to the customer for the drawing and the part, they said, here, I want you to inspect everything on this sheet. They'd look at it and say, where's the rest of the information? You only did one dimension. You did the 40 millimeters, and that's it. So obviously not complete, but it gets you on the right ballpark or on the right path. And that's where you now, okay, well, what's next? Okay, so let's say we did 35. Well, to measure the balloon number 2, we'd have to build this feature, which is a sphere, I think, which we've never done before. Turn the window off, the report window. If we want to build the sphere, we can go shift, build a sphere. I'm not going to change any of the settings here. I just want to show you there's a sphere. It has an X, Y, Z, and it has a spherical diameter. And then all I would do is distance. The distance between my circle E and my sphere in 2 dimensions, because I want to flatten that out. So from here to here, flat, not on an angle, is balloon 2. And look at that, it's 35 nominal plus or minus 0.4 tolerance from my title block. Balloon 2. Balloon 2, no spaces, no special characters, 0.4, 0.4, 35, create. Now I've created balloon 2. Can we change the profile as well in between the program? You absolutely can. So there's times where you have a very small feature on your part. So the one I have in the classroom on machine 6 is a good example. Most of that part I did with a 4x50 because a 4x50 is really robust. It doesn't break easily. And then I have tiny holes on there. I think they're 60 thou or maybe 80 thou in diameter. I'm jumping to imperial, I know, but I kind of remember the drawing on that as an imperial. So I know my 4mm tip doesn't fit down that hole. I need a different tool in order to do that. I change my tool right here. Boom. I've introduced a new tool. It'll tell me, okay, load probe 4x50 now. That's a bad example because it's the exact same size, but let's do 2x20. So now it's saying, okay, well, I want a 2x20 probe used in the future. So now it's a tiny little probe, and you can continue programming with that tiny probe. So you can absolutely, that's the benefit. And then if you have a tool changer, a rack at the back, it'll go and it'll change the tool automatically, grab a new probe, just like a CNC machine would, change the tool, come in and do the rest of and continue programming or running the program, executing the program all automatically. And I'm going to delete these again because I don't want to show you that right now. So I said we're going to do balloons 1. I did balloon 2 as a bonus. And we're going to do 8, 9, 10, and 11. Okay, so let's do 8 now. What do I need to measure 120 millimeters from the left side to the right side? What does not exist in my program right now in order to get this value? I'm asking you guys, so I hope someone can tell me. This exists, right? It's plain C.
But the right plane does not exist.
Right. That surface doesn't exist yet.
Yeah.
So the trick here is you could make it a plane. You don't need to, because you can go from a plane to a point, and you can just get the distance between those two. So if you don't need the flatness or the perpendicularity or anything that requires a plane on that surface, you can just make it a point. So let's take a look on the right-hand side of this drawing and see if we can identify a geometric tolerance like flatness or perpendicularity. So I'm going to go through the other sketches or the other views here and see if I can find anything. Right-hand side's nothing. That's a cross-section. Right-hand side, that's a cross-section. Right-hand side has nothing. This is my right-hand side view. This one right here. And it has true position of the holes and no other callouts, so just positioning. So that doesn't require a plane. And then I have nothing on the right-hand side here. And I have parallelism. So parallelism, can I have a point parallel to a plane?
No.
Exactly. A point can't be parallel to a plane. Only a plane can be parallel to a plane, or a line can be parallel to a plane, but properly it's a plane parallel to a plane, especially when this is parallel to datum C. So this needs to be parallel to this. So I now know that should be a plane, right? It shouldn't be a point, or I'm just wasting my time with the point. So that answers the question on how to build this feature on the right-hand side. I know I'm now scribbled all over this drawing, and I'm not entirely sure I know how to undo it. There we go. This Control Z worked. I'm now going to build a plane to represent my right-hand side. So how am I going to do it? I know the answer. I'm waiting for you guys to tell me it.
New alignment, sir.
Pardon?
New alignment.
No, I just need a plane.
We can just go into that DCC mode and select the
3-point.
3
And
points.
I'm already in DCC. I'm just adding a new feature into my routine. Just shift, click, and I have it.
Yes,
And you
sir.
could name it. Right. And plane. Okay. And we change our settings. Let's make it match what we've done with everything else. 5, 5. That's an awful lot of points for that small surface. Because the surface is smaller, I could probably get away with less points. This as that's why you might want to decide less points on here, but more points on here, because you're talking about point density. And then I'm going to keep my boundary offset at 2. And I'm going to click OK. So now I have a right-hand plane. I have a C. What do I do next to get the balloon? So I'm looking for balloon 8. Is that a distance, a position? Is it a dimension? What is it?
Distance. Dimension.
Yeah, it's a simple distance measurement. So you go to your dimension toolbar and select your distance dimension. And then you name it, the balloon that matches your drawing. Balloon 8. And you pick your features. So I got plane C. Do you want to make this a default ID? So every time you do a distance, it's gonna automatically make a balloon. The problem is the distance will be a balloon, but not everything will be. It doesn't work correctly all the time, but it's still a decent thing to put in your default because I like everything to be called balloon. So I say yes. So between C and my right-hand plane, I have to know my tolerance, which I forgot to check. Normally I have one side by side. I have a paper copy when I'm programming and I don't have to jump back and forth, or I have another monitor, but I'm trying to share everything on one monitor, so I'm jumping back and forth a lot. 120, no decimal places, which means I am plus or minus 0.4 tolerance. We agree? So that's not correct, but my X value shows 120. So 120 is my nominal, plus or minus 0.4. Balloon 8, click create, and click close. So now I have, if I went to my report now, I have balloon 1, balloon 2, and balloon 8. It's weird for you to jump. You should go balloon 1, balloon 2, balloon 3, balloon 4, but it depends how you ballooned your drawing, quite frankly. So this shows me now the nominal was 40 mil on balloon 1. The tolerance was plus or minus 0.4. It measured 40. Well, it measured 40 because it's a nominal, it's a CAD model, so everything's going to show perfect. I can run this in the classroom and I'll show you that the measured actual values are different. They have deviations. Some of them are not even in tolerance. So it's not always a compliant part. If you see out of tolerance, that's where you say, okay, there's a problem with this part, and I need to tell the customer this part is unacceptable. So it gives a nice red bar here, which I can only show online as well. It'll be red because it's out of tolerance, either large or small, or plus or minus. And the variance of from nominal will show in different colors. So a good measurement right near the middle is nice and green, and then you get dark green, and then you get yellow and red. You can change default reports and stuff. We're not going to play with any of that. You can play with these if you want. Just don't ask me to reset your defaults if you play with them. So if you do a change and you play with it, know what you're doing, because I forget which one is their default. Edit report. So text and CAD is a cool one. It shows you the actual datum with the labels, a solid model with the labels, and then you can kind of see. There's CAD only. This one is pretty cool because it just shows you a visual of that bar. I don't remember which one we were on though. This one's also pretty cool. So it's like a heat map. Everything's going to show good because our parts are perfect right now, but your features are going to show up in different colors if they're farther out of tolerance. I've never used that one. Plain text, sometimes people prefer this. This exports to Excel really well. So if you have some sort of statistical process control monitoring system, sometimes just Excel is the best version of the information. So you can plug this in when you have thousands of parts and watch for your statistical process control. And what one was I on? This one, okay. So just on, I don't know what it's called. Text only. So that's my favorite report, just because I feel like it has everything. My second favorite is the one with the CAD model. Text, toggle your window off again. Anytime you make a change to this, you need to toggle it on and off in your report window. Okay, so I want to get into constructed features now. That's the main thing, because it's in our PowerPoint for this week. We did this. Constructed features. We need to build features that don't exist, like the center line. So if I'm going to dimension and inspect for this 25, which is number 9, I need to build this center line, right? So how do we build it? Well, we need to measure this and build something in between. So it's a little bit tricky, but it's not impossible. So let's try this. Okay, so first of all, I'm on my left-hand side, and I'm in a geometry where I clearly cannot access that with an A0, B0 angle. I need to change my tool angle. Okay, so what should the tool angle be to measure inside of here?
A90, B90, sir.
A90, B90, perfect. Well done. So we go tool angle, A90, B90. Now I have the appropriate tool angle. And now this is what I didn't show you. We could just program this with program mode, because it's probably the easiest option. You just toggle program mode on, you click a point, and you click end. It's really quite that simple. You don't have nearly the flexibility you have if you did auto features. Here's an auto feature toolbar where you can select down, drop down, and select the exact type of auto feature you're trying to use, because the shift feature isn't as obvious how to get a point. It's actually really hard to get a point. I don't know how. So you need to go to auto feature, drop down, and I want to make a point. You could make it a plane. Okay, let me back up. Let's try to make it a plane first. So this surface to this surface, we want to make a plane. Hold shift, make it yellow, and drag across. Okay, I got this cool plane here. Anyone see any issues with my probe tip? If my probe tip tries to hit there, it's clearly going to interfere. So if I went to this and I changed my boundary offset to 2, like we've been using, well, that's a boundary right here. This surface is a boundary, and I'm only 2 millimeters away from that boundary, which means I'm right against that boundary because I have a 4 millimeter tip. So the only real way to measure that feature is to use a smaller probe tip. If you wanted to build it as a plane, you'd need a smaller probe tip to program that. Because if I change this to 2.2, for example, yeah, that works, but it doesn't give me a lot of clearance. Maybe I could change the number of rows to 2. But this is why you start to decide how you're going to program a feature. Pardon me, I gotta. Sorry about that. That's why I'm not in the classroom. Part of it. Okay, so I hope you guys can kind of see where I got to there and why. Okay, well, there's a plane here, but you have 2 points that are 0.2 millimeters apart. It's not going to really represent a plane. It's going to be kind of a fake, tiny little thin plane, and it isn't really going to represent that surface very well, right? So we could use it a plane, or we can do the points. So I'm going to do a point, auto vector point. You click that, you get the auto feature toolbar, and you can click on the surface you want to make the point. What I like about this feature is the avoidance move. You can change these from the default. Yours are going to be at 10. 10 makes that really close to the other side. There's not enough clearance there for when it comes in and it retracts. It's almost hitting the other side. So it's better to make this smaller now in this example, where it pulls that tool path in closer to the part. Click create, and then we could do the exact same thing on another point. We click create, and every time it's adding a point to my routine, I can click a point here, create, and click a point here and click create. And I have full control over how those points were made rather than when I do measured featured points. I'm going to click close. I have these 4 points. That doesn't allow me to measure from the center to the top, which is what I'm trying to do with balloon 9, right? Balloon 9. So I'm not done yet. I need to build the center line. So now I'm going to construct it. And take my points. And I thought I could do this by making a line from here to here and a line from here to here and then make a line in between. You can't do it that way. I always forget that. But what I'm going to do is I'm going to make a center point. So I'm going to do a point. Oh, sorry, I didn't really show this. This is the constructed feature toolbar, which is fairly intuitive to use and works really well in automatic. You drop down, we're going to make a point. Constructed point, okay? Everyone with me? Anyone with me?
Yes, sir.
All right, good.
Yes.
Constructed point. And we're going to take the 2 points. We want to make a point in between. Auto is usually pretty good at guessing what you're trying to do. So I want to take 0.2 and 0.5 and make a point in between there. 0.2 and 0.5. And when I select it, I can say I want it to be a midpoint. So I want a midpoint between them. Or I can keep it on auto and see what it does. It made a point right underneath. It's underneath my probe tip right now, so it's hard to see. But there's a point right there floating in space. Obviously, I can't measure that point. The only way to do that is with a constructed midpoint. And now I'm going to make another midpoint between 3 and 4. So go back to my constructed feature, make a midpoint between 3 and 4. And this time, let's pick midpoint, even though it did that automatically. Click create. And now we have a midpoint. And now that doesn't give me a center line yet. I then need to go constructed line. And I want to use my constructed point and my constructed point to make a line. And now I have a line there. My line 2 is a line floating in space that never existed before. And if I look on my routine, it's orange because it's constructed. So there's no way to measure that. It has to be created. But now I have a line that should represent my drawing center line. This line right here. So now I can measure the distance between those two surfaces. What is the top surface called? Right here. I'm waiting for an answer.
Plane A.
Top is A, right, sir? Datum A.
Exactly. So we got datum A, plane A, and then we have our line 2, which was our constructed line.
Sir,
See how the labels are starting to get a little messy here? So we have line 2. So now we just need a distance between those. Distance, dimension. We're going to mention distance, and we're going to say balloon number 9. Don't trust your ID defaults. They're not necessarily correct. And we're going to go from line
Line
2
plane A.
to plane A. Our dimensions look a little funky. Let's see why. It should be 25 mil. So our nominal should be 25. Let's see if I can sort this out. 3-dimensional. If I go 3-dimensional, it goes to 25 mil. Our tolerance is plus or minus 0.4 because there's no decimal places. So now my balloon 9, I mean, is programmed. And I'm going to click create. I'm going to click close, and it's now toggling on my report window. Now it's built into my routine here. So technically all you have to do when you're running that and executing it is 4 points are taken, and then it's going to build everything else and tolerance it. That'll all happen just instantaneously in the software. But it physically has to make those 4-point contacts because they're measured points. So it has to physically find where they're located. So that's dimensioning, and that is constructed features. What we have left to learn today, and basically left to learn in the course, is datum labeling and geometric tolerancing. So we'll take a short break, come back, and we'll do datum labels. And I will pause the video for the break, but if you have any questions, stick around and I will I'll try to address your questions. If they're good, I will probably, or really good, I'll probably incorporate them into when I actually record afterwards. But if you just want to clarify a few things, if I went too fast on a couple of concepts, you can let me know and I can try to help you out during the break.
So can you repeat balloon 9? Balloon 9.
I can from the beginning or from where?
No, sir. In the distance, from the distance, sir.
Okay,
In the
because
dialog box.
I went to select my two features, line A and line 2, and I made the number 9, but I have now created 9, so I need a new name. I'm just going to add a letter just for the fun. Now, I can't get the correct nominal if I go here, or I go to the feature, or I go to the X, or I go to the Y. So the nominal we know from the drawing should be 25 millimeters. And I don't see that value, which kind of concerns me. Well, now, if I'm being completely honest, I just don't fully understand 2-dimensional and 3-dimensional and when to choose it. I just know that it's pretty easy just to toggle between the two and see if you get the right nominal. I wish I could explain it to you better, but I don't know how, and that's just the honest truth. I know that I can get the right nominal. I don't know exactly how to explain the why. So by changing it to a 3-dimensional distance type, I am able to achieve the nominal in the tolerances of 25, which matches my drawing. So now I know it's looking at the criteria correctly because the automatic nominal is coming up correctly. Is that good?
Understood. Yes, sir. Yes, sir.
I'm not
Thank you,
going to
sir.
hit create because I already have it. Name must not, I hit close. I don't know why. Okay, there. All right, so 10 minutes. Let's come back at 5:10. Then we'll do datum labeling and we will do geometric tolerancing. Okay, I'll see you at 5:10. All right, so just so you guys know the remaining weeks of our course, what they could primarily look like. We have 2 weeks to work on a project together. This is a group or paired project. Do you need 6 hours to program this? No, you probably do not. If you're good at programming, you can do most of the criteria for this within one class, almost certainly. That extra class is there. If you need it, I'm around. It's basically open class time for the project. I will open these because there's no reason for them to be hidden now. But we have a lab 4 next week. So not only are we working on our project, but we'll be working on our remaining lab. I'll give you the details next week, not now. And we have our final exam week 15. So what this looks like is week 12 next week, we have a lab and we're starting our project. Week 13, we have a lab and we should be finishing up our programming of our project. If not, you must absolutely have it ready to go for your time slot on week 14, where you're going to be running it on a machine. This is a full hour for you and your partner on a machine. There will be no additional time, but you will get the hour to run and execute your project. It will include calibrating a new probe. So you need to make your own probe file and you need to calibrate your own probe file in with all the tip angles that you need. So this is essentially starting up, building a program, building your probe file, calibrating your profile, and it'll culminate kind of everything that we've done, and you need to do it independently with your partner. The criteria is inside the project, so you can already look at it and you can kind of get familiar with what the criteria are for that project. It's fairly extensive to mark, so it will be very difficult to have those marks in before your final exam, but I will do my best. And I'll take more questions on that next week. I just wanted you to understand what the remaining classes look like. Okay, so what we're doing here is standard dimensions. We're doing position. You could add a position tolerance in here. There's not a ton of good examples on this drawing. Let me see if I can find one, but just a plus or minus. These are GD&T. This is basically the closest thing we have to plus or minus. You'd have a 30 and a 40. Oh, we can do this one. Okay, so we'll do this guy and this guy. So we are at the same time able to inspect 40 and 30. So this would be, and then in a different world where I balloon this drawing differently, this would be balloon number 2. Then this would be balloon number 1 because they're related with an X and a Y value. So we already have these. Let me delete my balloons 1 and 2. And I would go position tolerance or location, sorry. That is true position. So location dimension. We pick our feature, which in this case was that circle E. And we're looking for, there's 2 options on this featured location dimension. We can go auto for axes. We can create all of our dimensions in here. I am not a big fan of how these work. I prefer the more. When you go to more, it's very easy in this table to understand what's going on. You can give it the X, the Y, and the diameter tolerance all at once, which if we looked at our drawing, our diameter tolerance is right here. So we could also incorporate our diameter tolerances like balloon 3 if we wanted, but we're not going to. We'll do that we can do that separately as a GD&T feature. So that here, I'm going to uncheck diameter because I don't want to tolerance diameter right now. I want to tolerance X and Y. Balloon 1. And now that I said this out loud, I realized how that was a little dumb. It's the same balloon. So it's also balloon 1 and balloon 1. They're both balloon 1 because there is just an X and Y position. So 30 is my nominal on Y, 40 is my nominal on X from the origin. The origin is the alignment we had. So because I have this alignment, I can do it this way if I want to. Both are completely acceptable. It just becomes down to personal preference. My tolerance is 0.4. This is why I like the table because it's easy to enter those tolerances. And you just basically enter those tolerances, make sure you have the correct thing checked, and you click create. I did forget to, I guess, readjust the balloon number here. Oh, so this is a good, how do you edit it if you made a mistake? You double click, you change the name, for example, balloon 1, and then you must hit recreate. So you have to hit create, change it, and now it changes what exists already. Any questions on that one? Okay, so we've got about.
So why
Yep.
did you delete balloon 1 and 2 at the beginning?
Because I just wanted to do balloon 1 and 2 as the different style. 2 is technically still its own balloon now. I shouldn't have deleted it. I just thought that I guess I could have recreated these as balloon 12 or 13 or something. That was
Okay.
probably more confusing than a more confusing way of doing it. So I apologize.
Also, sir, can you please repeat it once again? The spear, like a quick review.
This sphere? This
No,
one?
no, the one which we created now.
Okay, let's pretend I didn't mess everything up then, okay? We're going to decide that this balloon 1, oh, I actually, in balloon 1, I could incorporate my Y position. So I forgot the Y position here. My Y position is part of balloon 1 because it's the position of this feature, the Y value and the X value. So this is what I should have done. I should have just said this is 1. Oh, and this is 1. So those are both 1 because they're both part of it. Then what I realized I did wrong, I had in here, whoops, I just deleted something that I shouldn't have. My sphere. So my balloon 1 previously was a distance, right? So I used to have this distance value from plane C to circle E, and I had tolerance like this. So this was my old value. I'm just restoring my program to where post break I was. I had balloon 1. I had a balloon 2 in here that I shouldn't deleted. I'm not going to recreate it.
Yes, sir.
So this balloon distance doesn't represent the X and the Y. It only represents the X. Do we agree? Just the distance from here to here.
Yes.
But I
Yes,
want the
sir.
Y position as well, because the drawing has a Y position right here. So what I actually did was I kind of dimensioned it wrong. Instead of a distance, it should actually be a location.
Okay.
So most circles are going to have a location. So I click location. I would call it balloon 1, which I can't do because it already exists. So this is why I deleted it.
Yes,
I
sir.
can't recreate balloon 1. So first I need to delete my distance balloon 1. Delete. And then I can build it as a location balloon 1. Okay. So now that I have that, I'm going from circle E. So I'm looking for the position of circle E. I click circle E. I don't need to compare it to anything else. I'm just going, what's my position of circle E relative to my origin? So that's where it really matters what type of alignment you have, because circle E's position relative to an ADB alignment is X0, Y0, but it relative to an ABC alignment is 30 and 40, X40, Y30. But if I had an ADB alignment, my origin's right in the center here, and it would be 0, 0, and then it doesn't give me the right information. This is where you start to understand alignments a little bit better when you get into dimension examples like that. I don't know if you understand that one yet, but it's as we go through more examples that should make more sense. So I want my X and my Y position. I don't want my diameter, because the bottom line is my diameter is going to be its own balloon. This is going to be its own separate balloon later on, where the diameter is called out. So I have my 30 and 40, they have the same tolerance. So 0.4, 0.4, 0.4, 0.4, and I click create. And now I've recreated my balloon 1 as an X and a Y. If I looked at my report here, I see I now have an X and a Y under balloon 1. Okay, so that is standard distance and location dimensioning. They're pretty basic for the most part. If you feel like you're doing it wrong, play with the 2D, 3D, and the X and the Y features, and then till you get the correct nominal, make sure your tolerance matches your drawing, because not every feature is going to have a 0.4 tolerance. Okay, now I got to get to GD&T because this takes a little while, and this is where our lab comes from for next week. So if we have something like, so this example of constructed feature is kind of a bad example. I made these 8 cylinders, and then I made a bolt hole circle diameter. Just it's a hypothetical. Okay, what would the diameter of those circles be if it was a bolt circle diameter? Meaning, what's the center of all of those circles combined? Looking like that black circle right there. That's not a real thing you would do in this drawing. Okay, datum labeling. So, like I said at the beginning, if you remember, when it has something like plane A, it's called plane A. It has a title plane A, but it doesn't actually have a label in the software saying, okay, I recognize this as a geometric feature of plane A. We have to tell it that. So in order to do that, we need to first insert a datum definition. It sounds a little funny, but we're defining a datum. So we're going to go insert dimension, datum definition. Now, when we do this, I kind of might have touched on this in your class, but I'm not 100% sure. This datum's always going to go in alphabetical order. So make sure you select the feature that's supposed to represent that datum, and you click create. Now it's defining that plane A is datum A geometrically. So for everything, it's going to look at that as datum A now. Not just that you have a plane A, it's also a datum. And then you have B, plane B, create. Plane C, it goes to C, create. We don't have a D, we didn't bother measuring it. We have an E, but a circle is not a representation of a geometrical feature. It should be a cylinder or something like that. So we're not going to label circle E as the E. It should be a cylinder, which I can show you later on. But so for now, we've defined A, B, and C. Okay. Now that we have these datums defined in our routine, we could look at something like a feature control frame that has a reference. Where's a good example here? So this one here. So it's saying this surface has to be perpendicular within 0.15. Let's call this balloon 15. Just because I know I didn't use that balloon yet. I should go in order, but I'm jumping around a bit. So I want perpendicularity of 0.15 millimeters to datum A. So let's do that. We already have this feature built. We already have A built. So this should be an easy geometric feature to call out. We're going to go to our dimension toolbar, and we're going to look for our perpendicularity symbol. Perpendicularity. It pulls out your geometric tolerance window. Now, this is the part that's slightly confusing for some people. Let's first change our ID to match our drawing. Balloon 15, I said it was called. You now need to pick which feature you're checking perpendicularity from. So I want to know, is this perpendicular to A? So what is this? This is B, right? Or plane B. You can see they have the same kind of labels, but one is a datum label, datum definition, and the other is the ID. They're not the same thing. So we're saying is plane B, oh, in brackets, now it has a B beside it because it has a definition. Is this B? So we select it. Now it needs a tolerance. It needs one datum because you can't check perpendicularity to itself. So it has to have a value. Its drawing was what, 0.15? 0.15, I think the answer was. 0.15. Just check. Yep, 0.15 relative to A. So all we're doing is basically making our feature control frame match. If we hit the plus mark, we get an A. If you don't want A, you have to drop down and select a new value. If you select it again, you'd get B. If you select it again, you'd get C. We do not want B, so we have to hit the X. That matches our drawing completely. The T is for a material modifier. We don't have a modifier on that feature control frame. It's just perpendicularity 0.15 to A. So that's done. If we hit create, we now have balloon 15. We're going to make that our default as well. We're going to hit cancel because it's just now looking to build the next perpendicularity callout. And now when I go to the routine, it's here. And I go to my report window, it's here. I now have balloon 15. So plane B, it's tolerance. So it's only one directional because it's a geometric tolerance. Saying, is it in the zone of 0.15? And there's no deviation because we're in the CAD model. So it's perfect. They're perfectly perpendicular because it's CAD. Understood?
Sir, I have a question.
Yeah.
Sir, in CMM machine, if I go to the some GD&T like position or perpendicularity and
Yeah.
plug the plane, it means the in the 3D model, if I go to the practical, the CMM actually measure the GD&T tolerances. So I can be modify results, sir.
Can what be modified easily?
Like currently you are just changing the tolerances 0.001 to 0.15. So it's
So
only
can I
possible in
just
the
change? Can I just change this?
yes, sir. This is only possible in the 3D model, sir.
No. No. Like, can you only program GD&T if you have a 3D model?
Actually, sir, in practice, if someone give me the job from workshop and I just
Yeah.
measuring that, so I cannot manipulate the results, sir. Like
What I
this.
would do if I was trying to check perpendicularity and I was trying to do it quickly with the part someone handed me, I would mount it on my machine. I would take my joystick. I would make a plane. I would hit point, hit the check mark. It built a plane. Plane's 3D feature. If I then check the secondary plane, so then I'm going to
Yes, sir.
point on my second plane. I now have plane 1, plane 2. And all I'm going to do is then say, okay, what's my perpendicularity between plane 1 and plane 2? So plane 1 with reference to plane 2. I would have to label datum, one of the datums, so that I have a primary and a secondary. I don't even need an alignment. It's a quick check to do because you have two 3D features that aren't dependent on an alignment. So you really wouldn't have to overthink that. If you have any other things you need to do, you probably want to do an alignment. But if you're just trying to compare two quick, like if you're trying to check flatness, it's easy. If you're trying to check a plane a perpendicularity to another plane, it's easy.
Yes, sir. Got it, sir.
Okay. All right, let's do another more complex geometric feature. And I'm gonna choose this right hand pattern. This is one of the more complicated geometric features on this drawing. This is one of the more complicated geometric features you're going to experience in industry. There definitely are more, but this one's relatively complex. So let's go through that. Excuse me. Okay, so I have to find it on my drawing first of all. And here it is. So I have a 28, a 14, a 9, a 3 by 14. All of this information is in square boxes. What does that mean?
6 dimension.
Basic dimension.
Basic dimension.
Yeah.
Basic
Basic
dimension.
dimension. So basic dimensions, does that mean this applies?
No, sir.
In basic dimension,
Absolutely not.
no tolerances apply.
No tolerances apply. So do not mistake that and use the 0.4 tolerance on basic dimensions. If there's a basic dimension, it's because this whole, this number, this number, this number, and this number are constrained by some sort of GD&T. So you need to find the GD&T that relates to these holes. And this example, it's an exact same view, so it's easy. 8 times. Okay, there we go. Well, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 holes. So we have a bunch of things here. We have 8 holes with an 8 mil diameter, a unequal bilateral tolerance, meaning it's different positive and negative. And then we have true position. So that the X and the Y are constrained, or in this case, it's Z and Y are constrained. No, yeah, Z and Y are constrained because of the view. This is why I said Z and Y are constrained by our true position callout, which gives us a circular or cylindrical tolerance zone, meaning that that whole center has to be somewhere within that tolerance zone, and then it's going to build a circle. So, but that tolerance zone is defined by C, B, and A, which means CBA, I said this many, many times. If I'm going to measure CBA, a feature control frame with CBA, what must I do? Where's my origin in a CBA, or where's my primary datum in CBA versus an ABC?
The primary datum is C.
Yeah, so primary becomes C. More important than A is C. So in order to identify and recognize this, the way you do that is with an alignment. A CBA alignment. Okay? So do not inspect this as primary, secondary, tertiary if you have an alignment with a primary as A, or the data should be different. If you have a CAD model where everything's perfect, it won't be different, which is really kind of screwy with the head. You need to have a part that's physically different, and then your values are going to be different with a primary as A and a primary as C. So it's important that you program it correctly. So we're going to program a true positional call out on those 8 holes on the right-hand side view with CBA. The first thing we're going to do is a CBA alignment. Okay. So we'll jump to our program. We can keep everything we have already done because it was relative to ABC. It's all under our ABC alignment. We technically want to finish everything that we need to do as ABC, but I'm jumping a bit just because I don't have time to show the entire part. So now I need a CBA alignment. I already have C, I already have B, and I already have A. So this is easy. I don't need to reconstruct them. I just go new alignment. What am I going to pick first?
C.
Yep.
And then
C,
B and
the C,
And then B,
then B and A.
then A. So they're first, second, and tertiary. Primary, secondary, tertiary. Call it the right thing, because now we have a long routine. That's starting to get a little bit confusing. CBA, our recall is startup. So now we want to know everything after CBA or after ABC until what point a new alignment then applies. Once we see this CBA in our routine, we'll say, okay, if I need to measure anything with an ABC alignment, I have to do it before my CBA. I can't do it after. So I would add new information in here, new dimensions in here if they applied to ABC, but if they apply to CBA, I have to do it after. Okay. Now this is a cool feature, but you can't have programming mode on. So if programming mode is lit up here, go to your translate mode and select that. You're going to select a surface. If you see a pattern of holes on a surface, such as this pattern, you can select all that pattern at the same time with quick feature, but you first have to select the surface the pattern is on. So we know there's 8 times these holes. We want to do true position. It's a cylindrical tolerance zone, which technically means you need a cylinder. You can't have a cylindrical tolerance zone unless you have a cylinder. So we're going to select the surface and we're going to make cylinders. I'm going to zoom in and I'm going to select near the outer part of that feature and I'm going to click it. It's telling me to change the tool because we've already enabled auto wrist. This should have happened for you. If you do not see auto wrist turn on, hit cancel, and change your tool to A90, B-90. Then you don't even need the auto wrist feature. but you still have to select the surface and then the pattern. Okay, so I got a problem with that one, which means I probably have a problem with every single one of them, which kind of sucks. I'm not going to change the name of them. And I'm going to change my end offsets. I said that must be at least 3. I'm going to change my levels because 5 levels on a really short cylinder seems silly. And I'm going to change my hits per level to 5. And I'll leave it at 6, just because it's not a big deal. But what is a big deal is that they're in a quarter of the block. Now, if I hit check mark, the single check, it'll end that feature and move to the next one. If I hit the multi-check, all the same settings apply. If I hit multi-check, it's going to build all of those cylinders. So I just built cylinder 2, 3, 4, 5, 6, 7, 8, 9. No, sorry, yeah, 8, 9 with a couple clicks. So that's where it really excels to have quick feature. It's slick. But what we know is the start and end angles are wrong on all of them. For some reason, that setting's kind of weird. So I have to open each one and change my start angles from 0 to 360. Click OK, go to the next one, change my start and end angle. This is a bit tedious. I don't know another way to do this. Now, all I'm really done is I've built the 8 holes that are the pattern that I'm trying to inspect. Did it again. BYL 7. 360. But significant time saver versus program mode. If you try to create those 8 features in program mode, you got to click a point for every single time you make a point. So there's 12 points in every one of these 8 cylinders, which is you can kind of get the idea. A lot of opportunity for mistake. So it's really nice when you have. I think everything's good. Okay, so my features are nice now. I have cylinders 2 to 9 built after my CBA alignment. And now I can look at my geometric tolerance. So right here, technically speaking, this is its own balloon. So this is balloon. We're going to go with the next one I remembered. We used 15 last. We're going to go 16. And then the true position should be 17. Okay, now how to make the diameter tolerance on 8 holes and the true position on 8 holes all at the same time. Well, the software is really, really helpful for that. We need a C datum label. As you can see on our drawing, we have to have a C datum label, a B datum label, and an A datum label. And we already did that. We did C, B, and A. They're already labeled. You can see that from the tags right here. And C's over here. So we have our ID tags. So let's just do our tolerance now, the way that the drawing shows us to do it. True position. So we need a true position tolerance. Let's go to our dimension toolbar. And we're going to go to the same icon, true position icon. Now we're going to select the cylinder 2, because that's one of the 8 holes. And when we click it, we can see everything else disappeared, but these still remain, which happen to be cylinder 2, cylinder 3, 4, 5, 6, 7, 8, 9. If I just keep selecting, see this multiplier? It's just identifying that they're all potentially a pattern. So it's really, really handy. This is technically balloon. Maybe I was wrong about that. It's been a little while since I've done this. Balloon 16. 8 times 8 mil. It identified the nominal from the drawing, or from the CAD model, rather. So it knows 8 times 8 mil but we need to tell it that tolerance point plus 0.25 minus 0.15 plus 0.25 minus 0.15. Then we make our two tolerance. It knows it has to be a diametric tolerance zone because they're cylinders. So it's automatically coming up correctly. Back to the drawing. So we're having it right in front of you. It's nice and easy. We are 0.4 and we have a modifier, an M, maximum material condition, which meaning when those holes are the smallest they can possibly be, that's the tolerance that applies. As the holes get bigger, you're going to get extra tolerance. But the software can compensate for that. If the modifier is there, it knows how to do that. So what did I say this was? 0.4? 0.4, maximum material. And then to get the maximum material, you just hit the MC, and you can pick your modifying condition, M. And we pick the plus. Well, the first thing that comes up here is A, because it doesn't recognize what you're trying to do. It's most of it does, but this one you have to pick, drop down, it's C, make it match your drawing, B, and then A. And that should create our balloon 16. And I thought that it was 2 balloons. I must be mistaken. I'm going to hit create. I'm going to hit cancel because I created it. It's in my routine here. And then when I look at my report, I'm going to get very confusing results. Report. Balloon 16. Balloon 16 is a lot of information. I thought that they reported these separately, but it reports balloon 16 size and balloon 16 position. So that was my mistake. Technically, I could then update my drawing because this isn't 16. That's, sorry, not number 17. It's part of 16. Everyone still with me here? I know this is getting a little hard. I'm covering a lot of material. This is recorded at least, so you can at least rewatch this and catch up. Okay, so what's this mean? Balloon 16 here has a size. Cylinder 2 has a size, and then it has another size. Cylinder 3 has a size, and then it has another size. What this actually means, because it's a cylinder, it's going to give you the upper size and the lower size. So that LC is the lower size. So in case there's any misshaping on that cylinder, it's going to report it as 2. I don't know how to change that default. I've never seen or come across it, so I'm not sure you can. So you're going to have 2 dimensions for the exact same cylinder every single time. They all should be in spec. If it's not in spec at the bottom or the top, there's something wrong with that cylinder. It wasn't drilled correctly or machined correctly. And last but not least is my balloon 16 true position. This one, I love how they graphically show this, but true position is a little more complicated to understand because there's no X and Y or X and Z or Z and X. And in our example, it's Z and Y position. As you can see here, it's reporting as a Y position and a Z position. And then there's a measured value, what the actual position of that would be. But that position isn't necessarily a plus or minus like it would be in a standard dimension. It's true position. So there's a cylindrical tolerance zone. It's not a square tolerance zone. It's circular or cylindrical. So you get a bit of a bonus tolerance if the size is different. It'll account for the bonus and it'll report the position graphically here. I'll show that next week on the machines when I'm able to run it. But you're going to see each one, what the actual nominal X or Y and Z in this example, because the view I'm on, it's a Z and a Y position. And you're going to see all of your 8 cylinders in that pattern. Okay, any questions? We have about 5 minutes left, so I can run through that one more time, or I can run through that exact thing on a different example if you'd like. Or I can do a different feature. So if whoever wants to know something, whoever's the first to speak up is probably going to get the demo. If this starts to get too confusing to look at, you just hide them. They're still there. They're just not visually showing on your screen.
So it's getting too much confusing, sir.
I know that the GD&T part of things can be really confusing. What's
Like,
nice is that you kind of just need to make it match. And like building a cylinder, we know how to do. So if you have a requirement on a drawing, and we have next week to kind of, we don't have new content we're learning, and we're on week 11. So we have lots of weeks to reinforce everything we've learned so far, and to, if it's confusing, you have lots of time to kind of catch up and figure out what it is that you need to catch up on.
yes, sir, next
Um,
week, can we revise about the after the constructed feature, whatever we learned, can we revise it next week?
We can go over it again next week, yeah.
Thank you, sir.
After constructed features, it was all the GD&T.
Yes, sir,
So
definitely that part.
that's kind of what CMMs excel at, and that's their specialty, is being able to inspect that type of criteria. So if you don't know how to use it, then you're going to lack for sure. So it is nice to strengthen that, and I would like to strengthen that for everybody. Was it the pattern that I made here that was confusing, or is it using the dimensions?
So I mean, you did pretty well, sir. It's just that even
It's too much
before that, we added it, like we got to know like a lot of things. And on top of that, this GD&T just getting piled up, and it's getting too much of.
It's just too much knowledge for a one lecture. Just to
Yeah,
sum it up.
Yeah, sir,
that's
kind
fair
of.
enough. I'll take that
Yes,
into
sir.
consideration. There's if we were lucky, the auto feature stuff was done already, so we at least didn't have to cover that, but we did. I added really the dimensions and the constructions, right? Which is, it takes a bit of playing with to get really good at. And I guess you're just trying to be like, to memorize what it is I'm doing and the why. You really just need to think about your drawing. So like I would like to do another example, if that's okay. I got a couple more minutes, and maybe this will help. Or the more examples I do here, maybe it'll help you understand a little bit more. Where is the one I'm looking for? This one right here. So 26.93. So we're looking for an angular distance between those two holes. So to do that, what do I need to actually have? I can't check that distance if I don't know those features, right?
The axis, maybe axis of this.
Well, I just need this feature to exist and this feature to exist, programmed features, right? So does this circle exist or cylinder exist, or does this circle or cylinder exist? So you look at your program and you decide, does that exist? Sorry, does that exist? Does that exist? And then you can do your dimension.
No, so
So right now they don't exist. So we would have to build them. We go shift, and it's going to change the tool angle. We should know tool angles. We should know our end offsets. So this is nothing new. It's just practicing. And click OK. And then we click our second feature. We change our end offsets to 3. And then we have cylinder 10 and cylinder 11, and we want the distance between them, because our drawing is just showing the distance between them, right? This guy right here. Okay, so if I take my drawing, I now go distance. I pick those two features, cylinder 10 and cylinder 11, 10 and 11. I need my nominal to match the drawing, 26.93. So I should, it's not to the X, it's not to the Y, it's actually on an angle. So in this case, it's 3-dimensional. And there you go, 26.926, which rounds to 26.93. Click create. You have to give it a good label that makes sense. I didn't do that. Create, and you've done it. So it's once we know how to build all these features correctly, it's really just a matter of build them and then dimension them. So I know it's a lot. We'll strengthen it next week. I also want you to take the opportunity to rewatch the video or the component of the video that you struggle with, so you can fast forward to after our second break. So when I paused it for the second time, that's really when we got into GD&T. So at least that last 40-minute segment of the recording, that's probably the part you really want to rewatch. So if you struggle with the GD&T, I apologize if it's too much information for one lecture, but what I can tell you is that we have 2 weeks that we get to work on this in class and we get to build this together. We do have to have you need to have the capability of building an entire routine with a GD&T component. So you must know how for your lab, how to do a datum label and how to measure some sort of GD&T feature. The simplest of which is flatness, because there's no dependencies. I pick which feature I want to know the flatness of. I put a tolerance in and I click create. I can really check the flatness of any plane however I want. I'm just piling on more now, so I'm going to stop talking because I think that probably what I'm doing is just making it even worse, and I'm going to stop for that purpose. Okay. I hope everyone had a decent online class. I know it's a little different, but at least it gives you the opportunity to rewatch it this way and not me canceling class because I have COVID. So I hope everyone enjoyed, and I will see you all next week in person. Okay.
Have a nice weekend, sir.
You too.
Get well